Birmingham, and before this, Sierra fellow postdoc at Northwestern and had his PhD from MIT. Will Farr has works in general in astrostatistics, applied to a variety of things. For example, dynamics of exoplanets. For example, mapping exoplanets, denser systems, gravitational waves, and LIGO. He's a member of LIGO and the chair of the rates and population.
The co-chair.
The co-chair, sorry. And he wrote a textbook on functional differential geometry, which has 2 stars on Amazon. No, sorry, 2 likes for 5 stars on Amazon.
Oh,
so
okay. Oh my goodness.
It has 5 stars, but it's only 2.
Retirement is secured.
So tell us about gravitational.
Yeah, thanks for having me.
The lights.
What are we doing?
This,
Oh.
the lights. That, yeah.
Does this move? No, I have to move. Okay.
You can twist it. That'll help.
Okay, good. Now I can see everyone. Good. Yeah, thanks very much for having me today. I'm going to try to tell you about the emerging population of gravitational wave sources. As you just heard, I wear a lot of hats, but the one I wear most often these days is as the chair of the Rates and Populations group in LIGO. And that group, as a whole, works on understanding the rate of binary black hole mergers, binary neutron star mergers, neutron star black hole mergers, etc. from LIGO data, and also inferring populations, things like mass distributions and spin distributions, and then one step back to formation environments and how these exotic systems get started. My talk is really going to be in 3 pieces. The first piece is cool stuff about LIGO. Most of that is not something that I actually do. Today we're talking about gravitational waves and astrostatistics. But before I get to the cool stuff about LIGO, to motivate you to pay attention, this is the signal that started it all. We are a little bit past the anniversary. It was 3 years and a bit ago, September 14th, 2015. And it was the first ever detection of gravitational waves. This happens to be from a binary black hole merger. And we're going to work through this figure as a way of organizing a discussion about LIGO. But very quickly, what it's showing you is on the left, data from the detector in Hanford, Washington. On the right, data from the detector in Livingston, Louisiana. And you can see, because the Hanford signal is overlaid on the Louisiana signal, that these 2 detectors that are at opposite ends of the United States recorded something that looks pretty similar at almost exactly the same time. And I will talk a little bit more later about how we use that coincidence to build our confidence in these gravitational wave detections. Okay. So let's talk a bit about gravitational waves. I'm not really a gravitational wave theorist, so I'm just going to tell you the bare minimum of facts that you might need to know for this talk. Gravitational waves come in 2 polarizations. There are deep analogies with electromagnetic waves, and also a few differences. So gravitational waves are quadrupolar in nature instead of dipolar, like electromagnetic waves. They're distortions in space and time. So if you think about measuring space, say, by hanging something that's freely swinging along one axis, if a gravitational wave comes into the board, you will see one dimension shrink and the other dimension lengthen periodically, so you go from unperturbed to this perturbation and that to unperturbed. There is a second polarization where the ellipse is just rotated by 45 degrees. That's what I mean by quadrupolar. Dipolar radiation, the second polarization will be rotated by 90. And if you have a way to measure distances to these objects that are being distorted, you have to do it to phenomenal precision. We'll talk about that in a minute. But if you have a way to measure distances to these objects being distorted, you can read out the distance and make a plot very much like the one that I just showed. That's essentially what LIGO does. In order to get sufficient sensitivity, though, it's hard to do this on a tabletop. You have to go big. So LIGO instruments are interferometers. They're basically Michelson interferometers. But they have 4-kilometer-long arms. This is a picture of LIGO, the LIGO installation in Washington. That white building for scale is kind of the size of Penn Station. I used to say it's the size of New Street Station in Birmingham when I was in England, but they're pretty comparable. And that houses some laser apparatus and a bunch of vacuum equipment and a bunch of people who run the interferometer. And then those 2 arms you can see are evacuated. They're in vacuum. There's a laser that's split in a beam splitter in the building and runs down the 2 arms 4 kilometers to the end, where there are hanging mirrors that can respond to a gravitational wave. Laser comes back, interferes. and we see output in what is nominally the dark port as a measurement of the stretching of the arms. So these two sites are separated by 10 milliseconds worth of light travel time. So gravitational waves will show up in Washington and Louisiana at most 10 milliseconds apart. If they're coming straight down from above, they hit simultaneously. If they're coming in from one end, they hit one detector and then the other 10 milliseconds later. Anything that occurs in the detector separated by more than 10 milliseconds might be interesting, but it's not a gravitational wave. And we exploit that fact as well in the way I'll talk about it in a minute. Schematically, we have a laser that pumps about 20 watts into a partially silvered mirror, which serves the purpose of recycling the power that's circulating in the interferometer, to a beam splitter, runs down these tubes into a cavity that is tuned to capture the laser light with a quality factor sufficient to pump the 20 watts up to 100 kilowatts of circulating laser power. As the gravitational wave comes through, the test masses on the end of the cavity move. Because the light effectively makes many trips through the cavity, it builds up signal. So if the displacement of the mirrors is x and the quality factor is 10,000, this first approximation, the amount of displacement on the light is 10,000x. It's a way of boosting the signal. The light's recombined at the beam splitter, comes back out to a photodetector, and gets read out. The plot that I'm showing you in the upper right corner, if you've seen any LIGO talks, you've seen this plot. It's in our contract. We have to show it. This is the noise power spectral density of the LIGO detectors as measured about 3 years ago. So on the y-axis is strain noise. What we really measure is a dimensionless quantity, delta x over x, the fractional change in length. So that strain noise per root hertz. On the x-axis is frequency. You can see the peak sensitivity of the LIGO detectors is conveniently in the audio band. Okay, that's a function of their size. And in fact, we reach our peak sensitivity right about at 100 to 200 hertz. On the left side of that plot, the noise is rising rapidly because the Earth moves on hertz and subhertz timescales. There's a complicated suspension system with the mirrors that tries to isolate them. Stacked pendula, each one with a very low resonant frequency. Each stage buys you a factor of f squared as you couple them together. That accounts for the steep wall on the left. At high frequencies, we just can't get enough photons out, even though we have 100 kilowatts of circulating power, so dominated by photon shot noise. There's photon counting. And then in the middle, we're dominated by radiation pressure noise. The laser pushes on the mirrors and jitters them around. And so there's the seismic noise you can't do much about except to go into space, but there's a trade-off between this and that. As you pump more photons in, you reduce the shot noise, but you increase the radiation pressure noise, and so the spectrum can be tilted in various ways. And there's clever quantum tricks you can play to eliminate both noises at the same time. I'm not going to talk about it, but if you want to, you can Google squeezed light.
Just one question about that. I thought that the arms were like locked, so meaning that the real signal was not whether you see something at the photodetector, but whether the photodetector is giving control signals to
the real signal is the control you have to
It
apply
is,
to
okay.
keep the dark port fixed.
Okay,
Yeah. That doesn't actually matter for anything.
It
It's
doesn't
just a
actually.
cute detail. Yeah.
It's relevant to experimental design, though.
It is. And in fact, if you want, we could talk afterwards about originally the design was a heterodyne detector where the actual phase signal is plucked out through an RF modulation. And the new designs are homodyne detectors where the phase signal is actually read out directly by being a little bit off dark at the dark port. These are things I don't understand terribly well, but we could discuss. Okay, so what do? Most of the time, we are listening to noise in the detector. I'll tell you later that every 15 seconds, a binary black hole system merges somewhere in the universe, but the vast majority of them are so distant that we can't hear them. So most of the time, we just get that power spectrum of noise out, but we're constantly looking. How do we look? We take the data stream from the detector, and we filter it through template banks. We think we know what these in-spiral signals look like. They start out with a distant orbit, so low frequency and low amplitude. As the gravitational radiation carries energy out of the orbit shrinks, so the frequency increases, the amplitude increases as well, In a time domain, they sound like a chirp. I'll play some for you in a minute. We have banks, hundreds of thousands of chirps corresponding to different pairs of masses for the two objects and different spins for the two objects that form a filter bank. We run the signal from the interferometer through the filter bank, integrating it against these templates. When one of those integrals turns up sufficient strength in the data, we call it a trigger. We record triggers at about 1 hertz. So once a second, there's something in the data that rings up in this template bank somewhere at each site. When it rings up within 10 milliseconds at the two sites and for the same masses and spins, we call it a gravitational wave candidate. The interferometers are complex enough. They have a lot of modes. Okay? And a mode, a normal mode, that rings up and dies down can very easily mimic a chirp. So even with the coincidence in mass and spin and time, most of the coincident triggers are junk. So how do we say we've detected a gravitational wave? Well, we make plots like this. So these are a little bit complicated, but this is the detection statistic. It's a fancy name for the signal-to-noise ratio. Loud stuff, quiet stuff. And this is a cumulative number of events. The orange dots are what we're seeing in September 2015. So, thousands of coincident in mass and time triggers, decaying away to the loudest one that we saw, which is helpfully indicated with the little arrow, so you know that's real because I put a label on it. This black curve is an empirical estimate of our background. So the detectors are so complicated, you can't sit down and calculate how often they're going to fire off triggers. But what you can do is exploit this 10 millisecond light travel time. If you shift the detectors by a minute, you take the Hanford data and you just add a minute to its timestamps, and then play the two data streams together, there are no gravitational waves in that data. Can't happen. But there's certainly stuff that will trigger your template bank, make templates go pop.
So why does the red level off and the black go down? I mean, keep going down to a lower
The red, so in the black is this time-shifted data stream. There are no gravitational wave events in that data stream. There are only interferometer noise events. So the black is an empirical histogram of what you get by just running the same search you did on the real data, on this time-shifted data, literally billions of times. And it levels off because there's no loud noise events in the interferometer. This one stays here because that's a real gravitational wave. So we basically establish confidence. We run 10 to the 7 trials on pure known noise and never see anything this loud. That means that's at 5 sigma, a gravitational wave. There was another one. This is the one that occurred 15/12/26 in December. And then there's a marginal event that happened in October that is probably real, but the best we can say is it has like a 90% chance of being a real gravitational wave. That's how we build confidence in our detections. Okay. So now we've seen this pattern of wiggles. It matched a template in our bank. We believe it's some kind of compact object merger. What was it? That's the next part of this plot. So in the second part of this plot, we're now comparing our data to theoretical models. There's 3 models shown here. I'm going to go from the gray to the lighter gray to the red. Sorry, I'm going to start the light gray, dark gray, and then red. The light gray is an analysis that just tries to match correlated pixels in time and frequency. So little sine Gaussian wavelets, if you like, consistently between the two detectors. So it is, if you like, it's a non-parametric model for gravitational waveforms. All it says is each detector has to be doing something that phases up with the other one. But I don't put in any knowledge of GR. It doesn't have to chirp upward in frequency. It could chirp downward in frequency. It could be localized in frequency. I don't know what. I just want the two detectors to do the same thing. And if you extract what that waveform looks like, it's this light band. You can see it pretty well by looking at this part of the figure. If instead you say, I know general relativity, I know what black holes do, right? Black holes don't chirp downward in frequency. They go upward in frequency. They in-spiral and merge. So if you make approximate general relativistic calculations and ask what the signal could have been, you get that dark band there. So the width of that band corresponds to a range of masses that could fit the data, and a range of spins, and a range of positions on the sky, all the parameters you need to construct a gravitational wave.
Right? Don't you need to do this in the first place to get your trigger? You said that you had to match some templates.
Yeah,
with the
we
trigger.
actually ignore a lot of things, like phase, we just maximize over. We don't pretend that we actually try to fit the phase. The spins are only treated approximately.
So the template bank is simplified.
Rough and dirty.
Okay.
This is really trying to actually get reliable physical parameters out. But effectively, yeah, you kind of got to do that to find. So the first thing you can note, and this is like a sort of rough and ready test of general relativity, is that the models that didn't assume anything about gravity overlay pretty well the models that assume general relativity is right. And then finally, in the final test, so there's this red line here is a particular numerical relativistic simulation. So there's no approximations at all. You're just solving Einstein's equations directly with errors that are controlled in the way that one does when you solve PDEs. And that also overlays the data. It was chosen with initial masses and spins to match the detection.
On the light gray, you said that there's a requirement that these two be the same.
I didn't say the same. I said phased together.
Yeah, good, because I was going to say the two detectors are not oriented identically.
They are as co-aligned as you can make them on the surface of the Earth.
Right, but given that there's a non-trivial polarization, they will have different waveforms, right?
Yeah, so that is accounted for. You assume that whatever is coming in is some quadrupolar wave
so
that has an elliptical
It's really
polarization.
non-parametric in the polarized wave thing, and then it projects onto the data.
Yeah, that's right. That's right. You can relax that. In fact, a postdoc who works part-time at the CCA has relaxed that, and newsflash, we don't see any evidence for non-quadrupolar emission in any of these systems. That is also a test of general relativity. And at some level, conservation laws like conservation of momentum and conservation of mass. Okay, I'm going to skip this part and just say we can reliably extract parameters of these systems, masses and spins. When we do it for the first 3 detections, I'm calling this a detection. You see that's the one in September, December, and October. You can immediately see that there are strong correlations between the two masses. Gravitational waves, the shape of that wave, is primarily controlled by one mass parameter, has the dimensions of mass, it's called the chirp mass, that is a combination of the thing you really want to know, the physical mass of object 1 and the physical mass of object 2. So this narrow dimension here reflects the chirp mass direction, which we measure rather well, and this other dimension you can think of it as a mass ratio uncertainty. We don't measure that particularly well. So we get these bananas in the mass plane. The grayed out area is just because we always use a convention that M1 is the more massive and M2 is the less massive. We just label the black holes that way. In addition to masses, we can extract spins from these objects. It turns out that spin is highly degenerate with mass ratio. So this is the lighter mass over the heavier mass, 1 to 0. So equal mass, test particle falling into a black hole. And the spin parameter that we measure well is the projection of the spins of the two black holes onto the orbital axis, weighted by their mass. So M1, L1 dot spin 1, sorry, M1 L dot spin 1, M2 L dot spin 2, divided by M1 plus M2. It's related to the spins, but it's one parameter in a 6-dimensional space. Spins are vectors, so we don't get a lot of information about the angles of the spins. We don't get a lot of information about independently the magnitudes of the two spins. We really only measure this combination. However, for the event in December, you can see that we do not permit this combination of spins to be 0. There is no waveform consistent with those data that has 0 spins. this parameter must be at least 0.2. So perhaps both black holes were spinning at exactly 0.2, aligned with their orbit. Or perhaps one was spinning at 0.8 and the other one was minus 0.6 and they add up to 0.2. Or perhaps they were tilted in some way with big spins and project to 0.2. We don't know the answer to those questions, but we do know they have to be spinning. Okay, so that's the first really, first is a loaded word. That's the first gravitational wave concrete evidence for spinning black holes in nature. We can try to summarize what we learn about angles of spin, and you'll see why I'm talking about this in a minute, with these things we call these spin disk plots. We've got terminology for everything. Stop me if I lapse into jargon. These things are called spin disk plots. The left-hand side refers to the more massive object. The right-hand side refers to the less massive object. The radial coordinate here is the spin magnitude, and the angular coordinate is the tilt of the spin relative to the orbit. So if the more massive component is maximally spinning aligned with the orbit, it goes right there. If it's maximally spinning and in the orbital plane, it goes there. If its spin is 0.5 in the orbital plane, it's right there. And then for the less massive component over here. And you can see for the event in September and the event in October, this looks like some diffuse cloud. We have no information at all about the spins. Except that we don't like them to be maximal. This strip here around the edge is pretty well ruled out by the data. But they could be as high, you can't really read it off this plot very well, but I'll tell you the spins in these two events could have been 0.7 total. There's the data, it's fine. For the December event, however, you're seeing that phenomenon I was telling you about. The more massive black hole, at least, the origin is ruled out in that plot. You must have at least 0.2. We can't really tell whether it's like maybe 0.2 to 0.6 aligned, or maybe even higher magnitude spins tilted by as much as 45 or even 60 degrees. We just aren't that sensitive to the angular information. But we can tell that the more massive component in that system was almost certainly not spinning retrograde. Its spin is not misaligned with the orbit, to greater than 90 degrees. Okay, so that was just the first three. In fact, it's going to work. Yes. LIGO has published 6 additional black hole detections and, running along the bottom here, a binary neutron star detection that occurred last August. So we now have 7 gravitational wave events, 6 like these binary black holes, and 1 that is a binary neutron star. And not shown on this plot is one of the events, 1706-08, that happened in June. It was published much later than the other one, so it just didn't make the plot. Now I'd like to talk a little bit about the binary neutron star before I come back to the population of binary black holes. So here, this is the late stage of the binary neutron star. Strain, there's the merger. And that is what a gamma ray burst sounds like in the Fermi center.
Is that the actual time or is it stretched?
Sorry? That is real time.
It's
Not stretched at all. It's real time and real frequencies because it's audio. It merges at about 1.5 kilohertz. So it's kind of the upper limit of what you can hear pretty well.
But not for Fermi.
Not for Fermi. Yeah, gamma rays don't sound like anything. But this was the first gravitational wave multi-messenger event. Okay, it was detected in gravitational waves and in electromagnetic radiation. The first electromagnetic radiation seen was this gamma ray burst. The fact that that occurred 2 seconds after the gravitational wave merger tells you that the speed of light and the speed of gravity are very close to each other. In fact, the distance to this event is about 40 megaparsecs, or 120 million years. So 2 seconds over 120 million years is 10 to the minus 15. So c gravity minus c light over c is 10 to the minus 15, or smaller. When this event occurred, it was in the southern hemisphere. All the really cool telescopes are in Chile, and the sun was up. But about 8 hours after the merger, the sun went down in Chile, and we didn't just see it in gamma rays. So you can see there's a gravitational wave spectrum, there's the gamma rays. But we also saw it in the UV, in the optical, in the infrared, starting less than a day after, in the radio within a day, and in all of these bands extending. There's 10 days and out to hundreds of days, and even further. In particular, within about an hour or two of observing, 6 teams, here they are, the SWOPE, DLT-40, VISTA, MASTER, DE-CAM, and Las Cumbres Observatory, had taken images. This blob here is a galaxy, NGC 4993, and that dot is not present in archival data. That dot is about 16th magnitude and is the kilonova afterglow of a binary neutron star merger. And literally, like this counterpart, the location of the counterpart, was reported about 2 or maybe 2.5 hours after dark in Chile. So this was found about as fast as you could hope for. Yeah.
That 2 second, I mean, are you just kind of being facetious, or is there real physics in that 2 seconds?
Well, I mean, there's real there's some theories, right? If you have extra fields that modify gravity in some way, then you can get a dispersion relation as you propagate. You try to make like these fields of dark energy, and now you're propagating through them, and gravity gets a dispersion relation. The speed can be modified.
But the relation, if you're seeing at the origin, you know the relation of when the gamma ray burst comes out to when you would.
You know the gamma ray burst happens after the merger. You don't know whether, in fact, most models suggest much of those 2 seconds is not differences in speed, but is instead it takes some time to wind up some magnetic fields, generate a jet, drill. There's some dense cloud around the merger, and your jet has to kind of drill through it before it breaks out and produces gamma rays.
But I mean, so say that took 10 seconds. Does the theory say that 10 seconds would be off?
I mean, yeah,
One of the world's experts is sitting right
yeah, really, Andrew should answer that
Put him on the
question,
spot.
not me.
What's the longest time scale we could have? Because I didn't like 2 seconds. I was upset about it.
It's a
I
weird
was
amount of
upset.
time, and we're still trying to
Yeah.
understand it. But it's probably off axis, so it takes a while for the photons to get out. But the details are still.
What's the reasonable?
A reasonable time would be milliseconds because it's a small cloud.
It's like the dynamical time
Yeah.
in the cloud, which is,
And I said that on Twitter, and everyone piled on that. No, it's easy to do 2 seconds, but I don't think so. I
Yeah,
think
yeah,
it's not easy to do. 2
yeah.
seconds.
I don't really know about this stuff, but yeah, I guess that's hard. 10 seconds is correspondingly harder because it's, more dynamical times.
It probably means there was a supermassive neutron star for at least for hundreds of milliseconds that then collapsed to a black hole.
Yeah, and we looked. I mean, such a supermassive neutron star can generate gravitational waves. We didn't see anything, but our sensitivities are such that you probably wouldn't see anything. More advanced detectors would be able to detect gravitational waves emitted by some rotating hypermassive remnant before it collapses to a black hole, and would, conclusively answer that question, I guess. Okay, so this event was a bonanza. Something like 1/3 of the global astronomical community was involved in some publication that hit the archive like that day when it was announced. So I don't know how the journals organized all the refereeing. But anyway, this is what it looks like, right? Because we now know. So this is a lovely image produced by Sonoma State. They hired an artist to generate an image. She did a fabulous job. You can see everything in here. So the neutron stars are merging. These are the neutron stars at the center. You can see the gravitational waves rippling out. There's gold here in the accretion disk because one of the products of this merger, the neutron stars kick out neutron-rich material and synthesize heavy elements. It's our process, nucleosynthesis, which we think makes gold. You can see the nascent gamma ray burst jet coming out the axis there. This is really what it looks like. Yeah, okay. So with this event, it spent somewhere on the order of a minute in the sensitive band of the interferometer and described 1,000 to 2,000 orbits during that time, and we tracked them phase coherently. So now this mass parameter, the chirp mass that we measure rather well, we actually know to a part in about few times 10 to the 4. In fact, the dominant uncertainty on the chirp mass is pretty close to the unknown motion of the object in the galaxy redshifting the signal in a way that we cannot measure. So for astronomy, when was the last time you saw mass of 10 to the minus 4 precision? Now, it's not a mass you actually care about. You care about M1 and M2. We don't measure that mass ratio parameter very well. But you can see up there at the tip where they're pretty close to equal mass, you're talking about a 1.4, 1.35 pair of neutron stars, which is like the bog standard neutron star that everybody assumes merging. We can't rule out that it could have been more extreme mass ratio, so a heavy 1.6 on 1.15. The blue curve there is if we assume that these things are light galactic double neutron stars and they don't spin very fast. So that chi z less than 0.05 is an assumption about the spins of the object. Double neutron star systems are not observed to spin rapidly, so they have small spins. We don't know that. We don't measure that. We just assume. If you relax that assumption and pretend that they could be neutron stars spinning up to breakup for extreme equations of state, then you get even more degeneracy in the mass, and you could have had something that's as heavy as 2.6 solar masses on something subsolar mass. Nobody actually believes that, I think. That's not really a plausible astrophysical scenario, but that's permitted by our data. Okay, just to be clear. I was just chatting with the grad students. One of the things I mentioned is c to the 5th over g is a luminosity. It's 10 to the 59, a few 10 to the 59 ergs per second. That's a constant of nature. That's the gravitational wave luminosity of an object, any mass, whatever you want, a pair of objects, orbiting at, the last stable circular orbit before the plunge into their singularities. So gravitational waves are really standard candles. So we can use our knowledge of the masses, so it's not literally c to the 5th over g. There's efficiency factors, there's issues relating to spin. These are neutron stars, so you can't really get to the innermost stable circular orbit. Things are more complicated, but effectively these things are very standard candles. And we can use the observed gravitational wave intensity to measure the distance, the luminosity distance to the object, in this case to 15%. 40 plus or minus 7 megaparsecs. We saw that it's in a counterpart. We saw the galactic host. That galaxy, you can just, it's part of surveys. You can look up its redshift with phenomenal precision. So now division gives you the Hubble constant. CZ over D, okay? So this is the version of the plot that's Hubble's diagram. Gravitational waves give you this, 40 plus or minus 7 megaparsecs. Redshift measurements tell you that the recession velocity of the galaxy is about 3,000 kilometers per second. And then you have to correct for local gravitational perturbations that mean the galaxy's not really in the Hubble flow. These are called peculiar velocities. So you make some corrections, and you get an uncertainty on the velocity in the redshift. And this line, the slope of that line, is the Hubble constant. Now, I didn't stick it in my slides, but Hubble's original plot sits down here. That's sort of the typical Cepheid distances you can achieve even today are sitting, down here in the, let's say, maybe few to 10 megaparsec range. So then if you want to make measurements with supernova out to higher redshifts, you need a distance ladder. You have to take all these steps. There is no distance ladder here. These are self-calibrating. Now, if you translate our uncertainties into an uncertainty on the Hubble constant, it's actually, in the context of 21st century astronomy, it's a pretty crap measurement. Okay, this is the probability distribution for the Hubble constant, and the 1 sigma width is, 7 to 10 kilometers per second per megaparsec. On the other hand, that's from one event. So as we get more and more of these events, this uncertainty decreases like root n. Shown on this plot are the going favorites. This little green band here is the Planck measurement, which uses distance scales in the early universe. The orange band is the SHOES, that's the Adam Rees supernova measurement that uses local distance ladders. And you can see that they disagree. So this is the crisis in cosmology that's running these days. Gravitational waves from this event can't inform that, but put together 50 of these events, and you can. And we expect to get 50 of these events in the advanced detector era. So by the mid-2020s, we expect to be making 1-2% uncertainties measurements in the Hubble constant from a self-calibrated distance ladder. So that's cool. Yeah, here. This is the paper. You can see the archive. Note. Okay, so where are we? Well, LIGO's detected a bunch of black holes. Those are the blue dots up there. So this is the stellar graveyard. Mass runs up this axis, 1, 2, 5, 10 solar masses. The purple dots are the known X-ray binary black holes and their mass estimates. Down here, the yellow dots are known neutron stars and their mass estimates, and this is the neutron star pair that merged. At the moment, you can see LIGO is not the dominant source of objects in the stellar graveyard. But as the instrument gets more sensitive, in particular it turns on in February with enhanced sensitivity, we should be getting one of these every week or two, and one of these every month or two. So it won't be long before LIGO is dominating the population of stellar remnants. And that brings me to the third part of my talk, which is populations, something I'm deeply concerned with along with my colleagues. So I'm going to tell you about a few recent results that have involved me first, because I'm here and I'm going to brag. But then at the end, I'm going to switch hats, and I'm going to tell you about the young folks. I don't mean physically young, but academically young folks who are in the rates and populations group who you should be paying attention to. LIGO is hoping in the next couple of months to come out with the O2 populations paper. Everything you wanted to know about the black holes we've seen to date. And these are the people who are actually putting in the work to do that analysis in some way. So stay tuned for that. But first, me. Okay. So at the moment, with only, at the time I wrote this paper, 4 events, now with 6 published events, population questions are a little bit thorny. My normal reaction is to fit everything. Let's imagine we've got a mass spectrum and a spin spectrum. Maybe these things evolve in redshift. Maybe they're non-uniform on the sky because of the cosmic web. Let's throw it all in there. And you got 6 data points. So you have to kind of take a step back and think about what you can extract by being clever rather than just, fit all the parameters. And this story is about using the spin distribution of these black holes to say something about the origin of these systems. So it's thought that binary black hole systems form through 2 channels. One of them is forming in the galactic field. That is an isolated binary with high mass stars, goes through binary stellar evolution. High mass stars burn quickly. One of them becomes a giant and fills its Roche lobe and transfers some mass. That changes the orbit. One of them has a supernova or a direct collapse to a black hole. Its main sequence partner then goes through a giant phase. Now there's an envelope that envelops that black hole. They go through a common envelope. You get the idea. It's complicated, but you can imagine modeling all of these processes, and at the end of the day, you're left with 2 black holes in an orbit that merge. The alternative scenario, what might be called the dynamical formation scenario, is you have some dense stellar environment, a globular cluster or a nuclear star cluster in a galaxy, and you have ordinary high mass stars that possibly are even alone, or certainly maybe they have a companion, they don't interact much with their companion. They go through a supernova that makes an individual black hole, and now that's a heavy object. It tends to sink to the center of the stellar environment, and if it encounters binaries, it tends to swap in. Right? Heavier things participating in a binary single interaction tend to wind up in the binary, bump the light stuff out. So it's easy to have these repeated encounters that result in exchange, first of one black hole into a binary, that's somewhere along here, and then a second black hole into the binary, and then a merger. And for our purposes in this story, forget about all the complications. In this picture, the stars have been interacting and transferring mass their entire lives. And that means that whatever spin they have has likely been torqued into alignment with the orbit. And these black holes that merge, if they have any spin, it will be orbitally aligned. These black holes formed somewhere in a cluster of some kind and went through a tumble dryer, right? All these dynamical interactions. And by the time they ended up in a partnership, their spins are isotropically oriented. They don't know anything about each other. So one way we could hope to disentangle this population from that population is to ask, do we have isotropically oriented spins or not? Well, if you take a look at these spin disk plots, there's nothing really obvious that happens. They're all kind of blobby. We don't measure angles well. So if you try to fit an angular distribution from these things, the data is basically uninformative. However, there is that one parameter, right, the aligned component of the spin that we measure really well. And if we look at the aligned component of the spin, these are now the probability distributions for the 4 events going when I wrote that paper. If you look at the aligned component of the spin, it's small. Now, that doesn't tell you about angles, but it's suggestive. If I have black holes regularly spinning somewhat rapidly, and I put them through a tumble dryer, there's a phase space argument. Alignment has 0 phase space relative to spins in the equatorial plane. So if black holes are regularly spinning pretty rapidly, you can still see small aligned spins if you just tumble them around and let them align randomly. Now, if black holes don't spin randomly, we have no traction on anything through spins and the game is over. Okay. So those are the two possibilities. So if you run through some population modeling, there's this nice sharp edge. We can talk about that later. If you run through some population modeling, you compare various assumptions about the typical magnitudes of spins in the eye for isotropic and aligned for aligned, isotropic aligned, isotropic aligned. The best isotropic model outweighs the best aligned model by a factor of nearly 30. So if you like to think in sigmas, p is less than 0.05. It is socially scientifically significant preference for isotropically oriented spins over aligned spins.
And what are the F's, H's, and L's?
That has to do with the intrinsic distribution of spin magnitudes. This one's flat from 0 to 1. This one is high, it just linearly ramps up, so the average spin is 2/3. This one's low, it linearly ramps down, the average spin is 1/3. Note, though, that all of them have significant numbers of black holes with real spin. None of them have, 0.01. If the real spin magnitudes are all 0.01, we're screwed. This test doesn't work, and it doesn't tell you anything. So that's suggestive that we're seeing a dynamically formed population. And as we build up more and more detections, in the context of these models, we very quickly get 5 sigma, whatever confidence you want. So with another 10 detections, we'd have 5 sigma confidence in isotropy versus alignment. Okay, how am I doing for time? Good. Okay. Another series of projects have asked, what is the red? So that's about formation environment. Forget about formation environment. Let's just look at cosmic history. How have these things been merging over cosmic history? Or what is the redshift distribution of binary black holes?
Sorry, quick question. On your histograms, you have this Gaussian-ish centered around
Yeah.
zero. In the isotropic case, wouldn't they just be flat?
It's because that quantity is a projected angle.
Yeah, so it's just a cosine theta.
Yeah, it's a cosine theta.
So if cosine theta is just, cosine theta is uniformly distributed between -1 and 1.
So what you get is a convolution of the magnitude distribution, which is flat, and this is not an angle. This is like the
There's some
z
magnitude in it.
component. Yeah.
Oh, I see.
So these solid lines, if you had a flat magnitude distribution and the angles were isotropic, you'd get this blue curve.
Interesting.
There's also an issue that you're summing the two. So you have one isotropic vector and another
Okay,
one.
okay.
Yeah, so it's not so obvious, but you can work it out if you sit down for a minute.
Okay.
Yeah.
But
Okay.
I don't understand why you're saying that the isotropic thing is more favored than just having a low spin population.
I'm not. I'm saying either black hole spins are regularly small, or the distribution must be isotropic.
Right, but you seem to be emphasizing one of those two. So is there some prior for the spin distribution? Or?
That is a thorny question.
Yes,
So the thing that makes a black hole is the core of a massive star. If you take even a slowly rotating massive star and imagine it's like in rigid rotation, and you just take its core and collapse it to a black hole, you get a spin parameter of like 2. That is, the angular momentum would inhibit collapse. Now, if you turn on just a tiny amount of coupling between the core and the envelope, and from the envelope there is a very intense wind in the last years of these massive stars' lives. So you have a long lever arm there, you're flowing a lot of gas out to infinity. If you couple that to the core at a pretty marginal level, you can spin it all the way down to 0. So, the answer to that question depends on what you think is happening either like viscously at the core envelope boundary, or what you think the structure of magnetic fields looks like in the last 100 years of these evolved stars' lives, and nobody knows.
Sorry, aren't these big black holes evolving through a lot of, in other model, through a lot of random interactions with differently aligned objects?
They are, but once they're black holes, they're so small that it's very hard to torque them. You can spin them up or down with accretion, but you have to accrete a sizable fraction of the total mass of the black hole to do that. So you have to eat lots of other stars. If you're encountering one solar mass stars, you're a 10 solar mass black hole. You have to eat 10, and we just don't think that they eat stars like that. So once, in a dynamical formation scenario, once the spins are imprinted on the black holes, they pretty much just stay the way they are.
But the outcome of these mergers, so the mergers you have seen, what is the expectation of the spins of those mergers?
It's nearly all 0.7 in the direction of the orbital plane as they plunge.
So this is why I have a prejudice that they will be spinning, because I think...
Yeah, you're talking about second and third generation.
Because if you're merging 30 solar mass black holes, it wouldn't be surprising if they're multi-generational.
Maya Fischbach is one of the young people in the Rates and Populations group and has written a paper about second, third, fourth generation black holes. And the existing spin measurements argue against that.
I see.
Because the magnitudes of the spins tend to pile up at 0.7.
That's it.
And it's hard to get it so small. But it's not dispositive at this point. Yeah.
If you've got a small number of dynamical interactions, do you preserve any legacy of the three-body sort of orientations and so forth? Because the capture will depend on the alignment of the spins, right?
Very weakly, I think. To leading order at the gravitational interactions that are happening in a cluster, these are just point masses. The spins don't matter until you get really deep in the potential. Yeah. Okay. So at some level, it's a fool's game to ask questions about the redshift distribution of black holes. Because these dashed lines are the sensitivity curves, if you like, that we have in O2 as a function of redshift. So this is the probability that a detected redshift will be less than some number. And you can see we can't really see 10-10 mergers beyond a redshift of 0.2. We can't see 50-50 mergers beyond a redshift of 0.6. But you can either consider this some kind of measurement of the local universe or a warm-up for design sensitivity, early 2020s, where you can see a 50-50 merger out to redshift 1.5. And then things get a little bit more interesting. So the piece of work that I actually want to highlight, here, is the first paper I listed there, Fischbach, Holtz, and Farr. There we asked, one of the questions we asked was, suppose that the redshift distribution of sources looked like distance to some power that isn't 2. Okay, so if things are just volumetrically distributed in redshift, then this looks like co-moving distance squared over E of z. That's what the redshift distribution should be. If you have unusually strong clustering locally, you can violate that. Or if gravitational waves don't think you have 3 spatial dimensions, but instead think you have 5 spatial dimensions, then their flux falls off differently with distance. So the distance we infer from the observed flux has a different power law relative to the volume than d squared. So we asked, can we constrain this power law exponent? You know, that gamma is chosen, so gamma of 3 is 3 spatial dimensions. And the answer is, well, here's the answer. You know, basically, we know there's 3 plus or minus 1 spatial dimensions from the 6 binary black holes we've seen.
I have other
Good
arguments.
news. But that is interesting. At this level, it's not really interesting in terms of a limit on modified gravity. But if you talk about gravity leaking into extra dimensions, when you have hundreds of detections, if this piles up at 3, you're placing a pretty strong constraint on whether gravity can actually feel extra spatial dimensions or not. Okay, I'm going to skip that. And then I want to talk about something that's very exciting. It's in progress. I'm just going to use my last bit of time on it. It's also with Maya Fischbach and Dan Holtz. And the idea here is, can you use gravitational waves alone to make cosmographical measurements, redshift distance relations? So what we did with the neutron star was the gravitational waves did the distance, the electromagnetic waves did the redshift. Can you do without that? Well, gravitational wave detectors measure redshifted masses. They measure masses from timescales. Timescales get redshifted. They measure m times 1 plus z. That's what we see in our detectors. So for an individual event, you can't do anything. Redshift and mass are totally degenerate. But for a population, if there's a feature at a particular mass in the population of binary black holes, then you will see that feature redshifting in mass space as you look further and further out. And there are hints of just such a feature. There's already hints of a maximum mass to black holes. And there's theoretical reasons why that might be so. There's a process called the pair instability supernova process. When stars get so massive that their cores are hot enough to pair produce, the radiation pressure that supports the core turns into producing only mildly relativistic electrons. The core loses pressure support, the star explodes so violently it's thought to disrupt the star. Effectively, this provides an upper limit, or may provide an upper limit on the black hole mass from stellar evolution. And that upper limit is pretty sharp. So let's assume it's perfectly sharp. And let's ask about the advanced detector era. So this is the early 2020s now. We're getting 500 black hole signals a year. Let's suppose they're distributed like some power law in mass up to a maximum cutoff, which I just placed at 37.5 solar masses, which is comparable to what people think might happen from this pair instability supernova process, but nobody can really calculate it exactly. This is what the population of detected systems would look like in dark from 1 year, in light from 5 years of advanced LIGO observations. Luminosity distances extend out to 12. That's redshifts about 1.5. The upper limit there is this sharp, you can think of it as an absorption line in mass space. The lower limit is just a selection effect. The signals get weaker as the masses get lower, so our horizon is smaller. But LIGO doesn't measure masses. LIGO measures redshifted masses. So this is what this actually looks like in the detector. This is m times 1 plus z. This is dl. And those lines are cosmography. The black line is the Planck 2015 cosmology. And the dashed lines are what you get if you change the Hubble constant by 10%. So you can immediately see that if you detect this population, you know the Hubble constant to much better than 10%. But interestingly, at redshifts of 0.5, the Hubble constant isn't the most interesting game in town. What's interesting at those redshifts is dark energy, right? The universe is transitioning from from matter-dominated to dark energy-dominated. So all of these things constrain h of z, right? The Hubble constant is a function of redshift. And if you put this population, and imagine you can measure the masses and distances perfectly, then you constrain the h of z curve like this. You get your best constraints at a redshift of about 0.5, which is a great place to be looking for dark energy. If you take this measurement and couple it to that percent level Hubble constant measurement from grav waves, which pins down this end, and use the CMB to constrain the matter density, which pins down this end in the matter-dominated era, then you measure the dark energy equation of state parameter to 5% in 5 years of advanced LIGO. That's if you can measure distances and masses perfectly. That's not what life is like. Oh, I didn't include a slide, sorry. In fact,
That also assumes that you have a super sharp cutoff. and
as
that's
long as the
like-
cutoff scale is smaller than, like, say 10%, like 4 or 5 solar masses, you can still see it well enough to determine its location.
Is there a good reason to think that it'll be?
In most models, it is that sharp because it's really pretty simple. It's basically related to the core density, which is all about the core temperature. It doesn't depend so much on the outer structure of the star. So even, over, let's say, 3 orders of magnitude in metallicity, where the outer structure of the star is changing dramatically because opacities there are varying a lot, the mass that you expect to be cutting the core off at is, changing by 2 or 3 solar masses. So it may well be that sharp.
But can't second generation mergers wash that out as well?
They can, but they tend, the ones that you see anyway, they tend to come from these high mass objects, so they still leave a gap. So if you take this plot and instead of treating these as dots, you fuzz them up with realistic uncertainties, you don't get a 5% measurement of W, you get like a 12% measurement of W. But that's still pretty sweet in the early 2020s. It's not quite competitive with like CMB stage 4, I think, but it's still a pretty nice result. So this is in progress, being written out. I promised to end with a slide. I put this in because we had a conversation at lunch about how large collaborations sometimes leave the people who actually do the work behind. So the whole past hour has been me bragging about things I've done, some with these people, but some not. So now I'm going to put on my hat. I'm in charge of the Rates and Populations group in LIGO. And these are the early career researchers in the Rates and Populations group who are actually going to be doing things in the soon-to-be forthcoming populations paper from LIGO. So there's the other Farr, who is a new assistant professor at the University of Oregon, Ben Farr. No relation to me, though we collaborate a lot. We've even been at the same institutes. Mike Zevin and Chris Pankow are at Northwestern. They have done work on the ejecta from these kilonova models. Chris Pankow is my co-chair of the Rates and Populations group, so he's actually the one who puts fingers to keyboard and writes these sorts of papers, the O2 populations paper. Maya Fischbach is a graduate student at the University of Chicago and has done work on, is there an upper limit to the mass of LIGO's black holes that we can already see in the data? The answer is there might be. Daniel Wysocki is a graduate student at RIT. He works with Richard O'Shaughnessy and does all sorts of population models in mass and spin space with all sorts of complicated regularizations because the parameter space gets too big. Colin Talbot is at Monash in Australia. He's done some really nice work on the possibility of having an accumulation of black holes near that upper mass cutoff, things that almost went para-instability supernova but didn't and pile up there. Simon Stevenson is now a postdoc in Australia. He was involved in the spin work that I was telling you about and also does population synthesis. He's built a code for synthesizing the populations of these objects with various recipes for handling the interaction between binary stars. Vaibhav Tiwari is in Cardiff. He's done some really nice work in estimating our sensitivity to these sorts of events, which is a fundamental quantity that goes into rate estimation. You got to know how much space-time you looked at, so you know the rate density. Ken Ning, Sebastian Gabel, Ricardo Buscio. So Ken Ning is at MIT. Sebastian is my ex-student at the University of Birmingham. Ricardo is a new student at the University of Birmingham. They also work in this group. They're all young, very young, like first-year grad students, so they haven't produced results. And I guess maybe some of you. So LIGO is an open collaboration. If this kind of work sounds fun to you, all you got to do is write an MOU and say you're going to do something useful. Welcome aboard. And I'm going to stop there.
Since it is 5 and we had some questions, I suggest we go to the reception and you can ask more questions to Will while having wine and cheese.
Cool. Thank you.